right, so Unit 8 is about acids and bases, and most of this is things that we covered last year, except for maybe the very end. It is divided up into 5 standards, so it is a longer unit than we've done in the past. All right, so the first section is on how we define acids and bases. So a little bit of history about acids and bases first. So they are typically defined as substances that change properties of water. So it all goes back to water and comparing things to water, because water is our neutral substance that we have. The Greeks classified them based on the way that they tasted. So if something tasted sweet, or sour, then it was acidic. If it tasted bitter, it was basic. Alkalis are known to neutralize that sour taste. And since we know that sour is acids, then alkali refers to a base. So sometimes you might hear an alkaline base or alkaline by itself, and it's referencing a base. So that's kind of where that term comes from. Lavoisier burnt phosphorus and sulfur with oxygen, and found that the compounds were acidic when dissolved in water. Therefore, he thought all acids then have to contain oxygen. Well, then Davy came around and said, wait a second, things like hydrochloric acid, hydrosulfuric acid don't have oxygen, but they're acids. So there was a little bit of debate there in trying to figure out exactly what is an acid. So then we have Arrhenius. Arrhenius said that acids produce the hydrogen ion or hydronium ion when they're placed in water. Now, you can use either H plus or H3O plus when you're talking about acids, as long as there's water present. If you're just giving a net ionic equation, typically you just see it as H plus. But either way it's written, it's okay. It means the same thing. You tend to find that people prefer one way or the other, although it doesn't really matter. So an acid in water produces the hydrogen ion. Bases produce the hydroxide ion. So Arrhenius, is limiting the definition of a base to something that has a hydroxide. What we found, though, is that there are bases that don't contain hydroxides. So his definition isn't a great definition when it comes to bases. So then we get Bronsted Lowry. Now, these were 2 different people who are working on this together, which is why they're both credited. The Bronsted Lowry acid is a proton donor. So if we look at our hydrogen ion that Arrhenius said it produces in water, the H plus, we know hydrogen has 1 proton. Neutral hydrogen would have 1 electron, but because it's got the positive charge, it's lost that electron. And then the most common isotope of hydrogen has a mass of 1, which means there's no neutrons either. So that's why we can say it's a proton donor, because the word proton there is referring to the H plus. So acids are proton donors, and then bases can accept that proton or accept that H plus. And so here we can see that the definition of base is a little bit broader to be more inclusive. So one thing that we did last year is that we labeled them in a reaction. So you have HCl as your acid, and it loses that hydrogen to form the conjugate, chlorine minus, and it turns into the conjugate base. And it's the conjugate base because it can reaccept that hydrogen that it lost. The Bronsted Lowry base accepts the hydrogen, so it's going to go from NH3 to NH4, and it turns into a conjugate acid because it can lose that hydrogen. So acid-base reactions tend to be in equilibrium because they can throw that hydrogen atom back and forth. Now, 2 definitions that you'll need to know is amphoteric and amphiprotic. Amphoteric can act like an acid or a base. Amphiprotic means that it specifically acts as an acid or a base by accepting or donating that hydrogen. So we have things that are acids and bases. They're called Lewis acids and bases that don't necessarily deal with the hydrogen. They deal with electron pairs. So a Lewis acid is an electron pair acceptor, and the Lewis base is the electron pair donor. So it's kind of opposite of what our hydrogen plus ion is doing. So amphoteric, you can act like an acid or a base. Amphiprotic specifically is talking about the ability to gain or lose a hydrogen. So amphoteric is more generalized. Amphiprotic is very specific to the hydrogen. All right, so you should be able to label acid, base, conjugate base. So in our reaction, I like to look for the acid first because that's the one that's usually the easiest to identify because it's starting with the hydrogen. So here we have HCl, so that's going to be the acid. Now acids donate the hydrogen, so when it loses that hydrogen, it's going to turn into Cl minus. And the acid turns into a conjugate base because it can reaccept that hydrogen. Now the hydroxide ion then is acting as our base. You can only have one acid and one base at a time. So the base accepts the hydrogen. So we have hydroxide turning into water, going from one H to two H's. So the base turns into the conjugate acid. Now this reaction has the arrow only going in the forward. That means the reversible reaction isn't going to happen. And that's because HCl is a strong acid, which means it dissociates completely. HCl will always give up the hydrogen. It doesn't want to gain that hydrogen. So that's why sometimes you're going to see the arrow going in one direction, while other times you might see it going in both directions as an equilibrium. It's usually only in the forward if it's a strong acid-base combination, and then it's in equilibrium if it's a weak acid or base. And we'll talk more about that later in the unit. All right, so let's look at this last example here. Notice that both of these start with hydrogen. What we need to recognize, though, is that hydrogen could gain water could gain a hydrogen, or it can lose a hydrogen. So it's amphoteric. So we're going to ignore that, and we're going to look at this species instead. And since it starts with an H, that has to be the acid in the reaction. Now it's going to lose the hydrogen. So it goes from H2 to H1. That's another way we knew that that formed the acid, because it's the one that lost the hydrogen. So it goes from the acid to the conjugate base, so it can reaccept that hydrogen. Water then has to be acting like our base, and it's going to accept that hydrogen and go to H3O plus or hydronium and form the conjugate acid. Please let me know if you have any questions.